says going live, so I think it's gonna get started. There we go. That should be all good. Thank you, Keith, for the reminder, and also Garrett too, and also Steve. Okay, thank you for the reminder. So now we got the DVR going, and we can just kind of focus on what we'll be talking about today. All right, so getting back to this homework assignment, the last part of this, um, it's just asking register A after the add instruction. So for the most part, this particular homework assignment does not need you to write a lot of code. The one that's due like maybe a minute ago. Um, but the swap homework assignment, does require you to do quite a bit of code. So I want to talk about that a little bit, just so that you guys have an idea of, how to write that code, because if anyone is trying to write that code entirely and then hope that it works and then just test it, that probably may not work very well. Okay, because I cannot even guarantee that I can write that code myself and get it working the first time. So what we'll do instead is we're going to write some code that relates to that program, but not exactly is going to do the same thing. I talked about a program before, the string length one. So I can do a string copy one today, because I think the string copy one, has some of the elements that you guys need to know. But at the same time, it is also a little bit different. In fact, it is a little bit more complicated in some way, because you need a loop or you need a recursion and stuff like that. So we'll go ahead and do that today. So I'll just do a string copy, and I'm going to use TTPASM as the extension. So TTPASM as an extension is really just my own extension to mean that this is an assembly source file, which means it contains all the mnemonics and not the hexadecimal code that you would load into the RAM component in Logisim. Okay, so we'll go ahead and get this started. Um, so we start with the Noarm instruction, um, just because we want to use the logic analyzer and to use the trace analyzer, not the logic analyzer, but it's very similar. Okay, my trace analyzer is modeled after a hardware device called a trace analyzer. So anyway, we start with the no op instruction, and then we do a JMPI to main. Okay, and then the rest of this program, at least for now, are really just comments to show us, what code we want to do in C. Okay. So the first thing we want to do is to find out, okay, what is string copy? Okay, strcpy. Most of you hopefully still remember this from CISP 360, your C++ programming class. Probably have talked about this. And string copy is the first one, not the second one. We copy the source to the destination, and it returns the destination. So whatever the destination is what it will return. It has a sample implementation of string and copy, which is not what we are trying to do. We are trying to do string copy, um, and you can definitely see that there's a problem here. We need to be aware of buffer overrun. We can also do string and copy if that is what people want. And let's go ahead and do string and copy because it's a little bit more interesting with just one more parameter. But the logic of it is a little bit more interesting with string and copy. So that's what we're going to do with this particular program. All right, so I'm going to get out of the man page and go back to the editor. So this time we're going to implement string and copy, and I'm not going to copy and paste the code on the man page just because I want to do it recursively again. Okay. The nice thing about doing something like this recursively is I can show you what the called subroutine needs to do to access the parameters, but I can also show you in the same subroutine how to call a subroutine and pass arguments. So it's kind of like a self-contained solution to illustrate both at the same time. Alright, so I'm going to type the prototype of the function. So this is string and copy. The first argument is the destination, which is just a char star or char pointer destination. And then the second parameter is the source. So in a C compiler, you can specify const to remind the compiler to check your code to make sure that you are not changing anything the source is pointing to. But in assembly language programming, the const is meaningless because there's no one to enforce that we do not abuse a parameter and start changing what the parameter is pointing to. So, but for just for the sake of making this match the C code or the documentation on the man page, we're going to do it this way. And now we can go ahead and implement the subroutine. So what I'll do is I'm just going to write the entire thing out, and then I'll comment out things as we go. Just like in the previous program, we're going to use a single line to do this. So we can say, let me see, let me see. This is going to be an interesting one. I can't do it with a single return, um, but it may not do what. Yeah, so a single return would actually work in this case, but it's just a little bit strange the way it is going to be set up. Okay, so I'm going to show you what I mean by that. So with a recursive implementation of string and copy, the first thing we need to do is to find what is the terminating condition. In other words, when do we stop the recursion? In this case, there are two conditions to stop the recursion. The first one is when n equals to 0. Because when n equals to 0 or 1, that means we only got one byte to copy. I would just use 0, so you will see why I would use 0 as a terminating condition. And then the second one is when the character that I'm copying from source to destination is the null terminator itself, because that's also how we can terminate a string and copy, is when we have finished copying the entire string. Okay, so we'll want to be able to specify that condition. Okay, so the first question to ask is, does n equal to 0? Okay, and if n does equal to 0, the first thing we do, we're going to just return destination without doing a single thing. So there's no action performed. We just say, well, I mean, we're just going to return destination because that's what the man page says it should do. Okay, so now we are going to use a nested ternary operator or ternary expression. The way the ternary expression uses associative property is it would put priority on the else condition, so we can actually daisy chain it. But instead of daisy chaining it, the usual way, I'm just going to put in extra parentheses, so this way it is pretty clear what is nested and what is not. So by the time we get to the nested ternary operator, it means n does not equal to 0. But since n is unsigned, not equal to 0 means it is greater than 0. We have at least one space left for copying. Okay, so in that case, we have we have a condition to evaluate, which is, are we copying the null terminator? Okay, so we want to look at source and ask, is the null terminator pointed to by source? Okay, if that is the case, we'll do the copying, and then we'll terminate. So in that case, we'll just say, actually, in both cases, we'll copy first. Whether it is 0 or not, we'll copy, and then one is going to do the recursion, and the other one is not going to do the recursion. So I'm going to specify that. So we say, regardless, we want destination to get whatever the source is pointing to. So now some people are going to say, Tech, you are going to have to resort to statements because there's no way to express sequential expression evaluation when you're inside an expression. Well, this is something that is really obscure. Some of you may know about this, and most of you may not know about it. It is called a comma. When you are in an expression, the comma is an operator. So what a comma does is, if you have a comma separated list as an expression, it will evaluate each expression from left to right in that specific order, and then the last expression of the list is the return value. Okay, so are we understanding this concept, or are there any questions?
Professor,
Yeah.
Professor, if it evaluates each expression in the list and then returns the last value,
Yes,
then what does it do with the other expressions? Am I missing something?
it simply just evaluates the other expressions without having those expressions to influence what the actual value of the expression is.
In that case, I'm not sure what the use is.
The use is something like this, okay? Something really obscure like what I'm doing right here. Okay, so I'm specifying an assignment operation here. And in other programming languages, in anything that is not C based, the assignment operation is called a statement. Okay, in other words, you cannot quite chain things easily with the assignment operation. But in C and C++, the assignment operation is an operator. So that means what you're seeing here, this part here, that is just an expression. Just like a plus b is an expression, this is just an expression as far as C is concerned. So now we look at this and go like, okay, we can now have another expression down here. So the next expression is also going to be something that seems to be pretty useless, because we can say if the source is pointing to the null character, then let's go ahead and do nothing. Okay, and when I say do nothing, I'm just saying, okay, let's just use a bogus value of 0. Okay, otherwise we are going to I can, well, actually with this one I can just say the correct return value is the destination already, so we'll go ahead and specify destination here. And then what we'll do next is to say, what if the source pointer is not pointing to a null character? Okay, so now we have another case here. Okay, this is another else. So in this case, what we know at this point where the white cursor or the gray cursor is at, is we know n is not 0, because otherwise we wouldn't be in this parenthesis. And we also know at the same time that the source pointer is pointing to something that is non-null, which means we are not quite at the end of a string yet. Okay, so there are other characters in the string that we might want to copy. So at this point, we're going to have to call string and copy recursively, because that's the only thing that we can do at this point. So we're going to say string and copy, we'll call it recursively. But then the destination is destination, my destination plus 1, because I have already used up that location on this line over here. So the substring that I'm copying, is going to copy to the buffer or whatever the destination is that is 1 byte off from my own destination. Source is the same way. We're going to add 1 to what source is the pointer of source, so that it is now 1 byte past what I was told to copy from. And then n is going to be n minus 1, because I have just used up 1 byte. So the number of bytes available for the recursive call is going to be n minus 1. So this is going to return dest plus 1, which is not what I want. Okay, so you have a few options here. You can say whatever it returns, just minus 1 from that, and that is what I want to return. That's one way to do it. You can also use a comma here to specify dest, at the end of this comma separated list. So that makes dest, or the destination, being the last thing that is going to return. So either way is going to work. So let's go ahead and do it the really kind of obscure way, is to utilize the return value of the recursive call and then subtract 1 from it. Because what the recursive call is going to return, we know for sure, is going to be dest plus 1, which is 1 byte past my destination, right? But my job is supposed to return my own destination. So my own destination is whatever the recursive call is going to return minus 1. So let me just kind of pause here and see if anyone has any questions. No questions? Okay. Does anyone want to question the sanity of this code? In other
Very
words,
much.
very much. Okay, I like that spirit. Very good. I like it. Okay. So what we'll do?
So
Yeah,
I
go
just
ahead.
want to confirm. So the reason this works the way it does is because the assignment operator is an operator. We can
Yes.
just say, "Hey, evaluate this expression." What this evaluating this expression just assigns this value.
Yes.
All right, ignore what the result of that assignment is. Go on to the next thing,
Unless it is the last one.
except for the last one, which
Except for
is
the last one.
Yeah.
Except, yeah, the last one is this one over here is this particular ternary um, expression. So that particular ternary expression is going to return just the destination if I just copied the null terminator. Otherwise, it's going to return the expression itself is going to return string and copy with dest plus one and then minus one, which is basically just destination itself. Are we good so far? Okay. So what I'm doing here is I'm just setting up a main so that this program would actually compile and I can test it. Okay, because I know some of you are saying this cannot possibly work. Okay, so I'm just going to test it. I have never done it before, so I'm guessing that it would work. Doesn't mean that it would actually work. So I am just uh, testing this, okay, and see if my understanding of C, is correct or not. So we also want to have a char pointer, which is storing the result because I want to see if the recursive implementation of string and copy is going to do the same thing as the original, the actual string and copy. So we're going to say result equals to string and copy, and we'll go ahead and specify the destination is buffer, and we'll do it the usual way first. Okay, give it a kind of well-formed string like ABC, and ask it to copy up to 5 bytes because there are several terminal cases that we have to test. But if it works in one way, I'm fairly sure it will work in the other ways. But we can always kind of test it separately as we go, or we can just do something like this and then specify the second one should copy only up to 2 bytes, and we have to make sure that all three characters are now different. All the source characters are different, so this way we can test how much of it is actually copied. We've got a few questions here. With n, we are passing in the char size of source. Yes, and I'm intentionally making it short. And then Hugh is saying n could be the size of source or how many char we want to copy from source. So the correct way, the usual way to use n is it would represent the size of the destination. In this case, it would be 20. Um, but I'm testing the code, so I'm not I'm not going to specify that. And then in the first test case, I am going to terminate using the null terminator after ABC. The second one is going to terminate because we ran out of length. And then in the third one, we'll simply terminate because the string is null. Okay, so it's not going to copy a single thing. Okay, so we'll test all three cases and we'll give it a try. So gcc-g to include debug information, and of course this name is no longer correct, so let's fix that name first. So I'm going to copy this or env it to string. So string copy should now be string and copy, and we'll call it .c because it really is a C program at this point. So we go ahead gcc-g -o string and copy, which is the name of the executable, and then string and copy.c, which is the name of the source file, and we want to include -1 all, just in case I do something stupid and the compiler says, hey, that is stupid. Okay, so the compiler does give me some warning, and it is complaining about on line 4 string and copy is declared in header. Okay, but I did not even pound include string.h. So the compiler is being a smart ass in this case and go like, hey, you might want to do this. No, I don't want to do that. Okay, so that means I am going to change the code a little bit to stop the compiler from nagging. Okay, oops. Well, it generated the output anyway, so I guess we can just go ahead and run it, but I want to make sure that it's not linking to the internal string and copy. So I would just make sure by changing all string and copy references to tags string and copy in this entire program. So this way, there's no way, there's no chance that I can accidentally be using the other string and copy, the actual one in libc. All right. So I'm just checking, making sure that we don't have any questions. You good so far? All right. So we'll go ahead and compile again. Okay, warn all. String and copy. We'll do a dash o first. Dash o string and copy, and then string and copy dot c. And it still complains about result not being used because we put a value into result in main, but then we don't read it you know after that, which is okay. That's an acceptable warning. All right, so we'll gdb the program, string and copy, and we'll put a breakpoint at the beginning of the subroutine because I want to see whether it's called recursively or not. So we'll put a breakpoint at the beginning of the function, and this is a shorthand to do that. You just say b for break, and then you just mention the label. In this case, is the name of the subroutine, and it will automatically put a breakpoint at the beginning of the subroutine. All right, so let's go ahead and run the program. So now we are looking at the breakpoint. This is the first call or the first invocation from main to text, string, and copy. And we can see that the source is pointing at the beginning of ABC, which is correct because it's the first call. The destination points to something that has some garbage in it, which is okay because it's not initialized. So now if we do a continue, it should go to the recursive call where the destination is 1 byte. Both the destination and the source should be 1 byte past what they are at this point, and then n should be decremented by 1. So that means destination should end with a 1, and then source should end with a 5, and then n should be a 4. So we continue, and sure enough, that happens. And we are not going to terminate at this point because none of the two terminating conditions is true at this point. Continue, and we are now we're copying the C in this particular invocation. It has to call itself one more time, which is the fourth invocation from the beginning, from where main calls text string on and copy. And now it is going to stop because we are running out of characters to copy. It is now pointing to the null character, which will stop the recursion. So at this point, okay, you might wonder, what is in the buffer at this point? Okay, so it really helps to look at the code again. So I'm going to list text, string, and copy so that we can actually see the code. Okay, so text, string, and copy is like this. So in order to get to recursive call, I should have copied something into the destination already, into the original destination. Except, I don't know where to get back to the original destination. Well, that's kind of a lie because I do know how to get back to the original destination because the original destination is here, okay? But there's no easy way to refer to that particular destination where I am at this point because we are basically 4 levels into the call stack. There are 4 subroutine calls at this point. Main calls text, string, and copy. It calls itself, and now there are 5 levels of call if you count main itself as one subroutine that is called. Um, so it is helpful to show you how to look at the stack at this point, but not in individual bytes, but in a much bigger logical unit of how many invocations of subroutines do we have and what are the parameters passed into those invocations of subroutines. The command to do this is called bt or backtrace, and you can use bt in code blocks and many other debuggers, many other IDEs, I should say, because they're all based on GDB. So it's just a command that you can type. So we can see from here that frame number 4, which is the most ancient one, okay, is main. Main calls string and copy. String and copies calls string and copy. String and copy calls string and copy, and then string and copy finally calls, guess what? String and copy again. Um, but we can also see that we can actually go back to main. Okay, we can go back to the context of main. So I can now say frame 4. So what this does is to tell the debugger and say, let's go back to the context of main. Now you have to specify the number instead of the name of the subroutine because you can see that text string and copy actually has 4 invocations. This allows you to pinpoint exactly which invocation you want to go back to. But I'm not interested in text string and copy at this point. I just want to go back to main, or the context of main. Okay, so now I get back to the context of main. And the reason why I want to get back here is I want to look at buffer. I want to, say, okay, what is in buffer? There are several ways to do it. Okay, most people can think of, let's just print buffer. In this case, it may not be the best idea, because if you print buffer, it's going to print it as if it is a null terminated string, which may not actually be the case because it may not be terminated yet. We have, let's see. Yeah, we have not copied the null terminator yet. Okay, we are about to copy the null terminator, but it's not there yet. So it is better off, to display the bytes individually using the examine command. So the examine command allows you to specify a count. Okay, so if you want to say, I want to print 10 characters, okay, you can specify 10. Then you can specify um, what each thing is. Okay, in this case, it is a, let's see, I am not 100% sure. I think it's a byte, and then each one we want to display as a character, and starting from buffer. Let me see if that works. There we go. That works. So it is printing from where buffer is, and we can see that we are looking at each byte as a character. So it's trying to interpret it based on ASCII interpretation. 97 is the hexadecimal. Nope, no, excuse me. It is not hexadecimal. This is actually decimal. So 97 is the decimal representation of the ASCII code of uppercase A, and we got uppercase B, we got uppercase C, and you can see how the null terminator has not been copied yet, because that's up to the 4th invocation to do, but the 4th invocation is right at the beginning part of the subroutine, so it has not done it yet. All right. So, are there any questions about how we are quote unquote debugging the C code? Okay, I'm not seeing any questions. All right. So we are gonna continue with this code. So one thing I am not sure, okay, this one I am absolutely not sure, is whether if I single step using the S command in GDB, does it treat each individual expression individually, or does it, if I single step, it would just go all, it would just finish the return statement because it is one single statement. In other words, is the granularity of a breakpoint, is it statement by statement, or is it line by line, so that if I break a single big statement into multiple lines, it would actually let me step through those individual steps? Now, this one I actually do not have an answer for, so we'll experiment and find out. Okay, so we say lowercase s for step, press the enter key, and guess what? It can actually get into different parts of the expression and set up breakpoints that way. This is really cool, because at this point I can now say, tell me what is source pointing to. Source is now pointing to the null terminator, and if you go back to the source code, you can see how, well, not quite yet. Okay, so because we on line 8 we're just copying, and now we have to decide, are we returning dest because source is null, or are we going to do the call recursively? So we single step again, and it says, okay, well, I think this means it's evaluating the condition. If I single step again, it should not go to the recursive call, because it should be returning the destination as the return value for this last invocation. So I single step again, it goes back to return, but I have no idea whether it's done with the returning of the 4th invocation, or are we now back to the 3rd invocation? So BT is going to tell us that. So BT says we're still in the 4th invocation, which means at this point both source and destination should be pointing to null characters. They're not going to be pointing at the same null character, but they should both be null characters. So let's double check that. So print whatever destination is pointing to, null. Okay, print whatever source is pointing to, it is also null. But if you look at print dest, okay, it's printing to this location, And if you print source, it's pointing to an entirely different location. So we know that we are done copying, including the null terminator. It is not recursively calling anymore, so the recursion is ending at this point. So do you guys want me to go through the entire program, or is this sufficient as far as demonstrating that the program does work? If no one is, oh, okay, Nick is typing. Okay, so but my question is still not answered. Do we want to continue with this program, or should we kind of go back to uh, the translating into assembly code part? I'm guessing we're okay. Angel is typing. Okay, so we can go back to the assembly code. If there are no objection, that's what we're gonna do. All right, let's go back to the assembly code. Cool. All right. So at this point, we know this code works in C. Okay. Now I'm pretty sure most of you have not seen, kind of a single statement like the one that we saw, basically using a ternary operator to implement if then, and then use the comma separated expression to implement a sequence of operations. In this case, a sequence of some of these are assignment statements, and then the other one is just a call. Um, but nonetheless, these are all features in regular C, but I think CISP 360 may not have enough time to explore these kind of really cool features of C. So what I'm doing now is I'm replacing, first of all the tab characters with 8 spaces, because the assembler does not like that. And then what we'll do is we're going to comment out all the C code and then uncomment the assembly code. There we go. And then save the file, and then we'll save the file in a different name. I probably should have renamed it first. There we go. And now we're editing the assembly code. The highlighting of the slash is because it's looking for it. So if we look for something else, it won't be highlighting those anymore. All right. Well, actually, it's looking for the beginning of each line. That's why the beginning of each line is highlighted. All right. So now let's go ahead and uncomment some code. This is the beginning, and we want to see how to implement the string n copy subroutine. So the first thing we need to do is to check whether n is 0 or not. But before we do that, okay, undo. Okay, there we go. Okay, there we go. We just say tags string n copy colon, and now we can specify certain labels. So this is kind of the same thing that we usually do. We have return address as a label defined to be 0, and then we have source defined to be 1. Now, if you want to say, but I really want to emphasize that source is 1 byte after return address, how do we do that? You can actually do this. You can say return address 1 plus, which is basically the same thing as in infix return address plus 1. It's kind of useful this way because in some way, oh, okay, it's not source, it's supposed to be destination here. And then source is destination 1 plus because it's 1 byte after that, and then n is source 1 plus. So I have now expressed the relative positions of all my parameters relative to where the stack pointer points to at the entry point of the subroutine. The stack pointer points to the return address. 1 byte after that is my destination, one byte after that is the source, and then one byte after that, which is the last thing, as far as this subroutine is concerned, is useful on the stack, is n. So at this point, we can now say, okay, so now how do we check whether n as a parameter is 0 or not? Okay, so I hope you guys do remember the trick. So we have a LDIA and then the name of the item that we want to access. So all this does is to load the offset to that particular item relative to the stack pointer into register A. So by itself, it doesn't really do anything particularly useful. Okay, so I'm not even going to bother to say what it does. And then we have the add instruction to add the stack pointer to A. So when you combine the displacement with the actual stack pointer, so now A finally has something that is kind of useful. It is the address of n, which is not what we want. So we can now say, okay, so let's go ahead and put it into a particular register. Um, I know we need n all the way down here, but I think there are not enough registers to save the values that we need to use. So we'll just go ahead and do a LD AA. So the A is now the dereference of the address of n, but that really is just n itself. Okay, so A now has the value of n, which means we are now ready to compare to see whether it is 0 or not. Okay. So instead of using yet another register to hold 0 and then do an actual CMP compare instruction, we learned that we can use AND AA, okay, to test register A. Okay, will influence both the Z and the S flag in the processor. And then we say JZI, okay, because the only thing we can test is whether the Z flag is set or not. There's not a conditional branch instruction to go someplace when the Z flag is not set. Or in many RISC architectures, they have conditional branch instructions with both polarity. So they actually have a JNZ instruction to branch when the Z flag is cleared or as a 0. But my architecture is a little bit lazier, okay, or it's more simplistic, so it doesn't have that. So we can say when it is 0, we can go to a particular label, and in the original code, that's the then case. So we can just say, just return destination. That's the name of the label. And my usual convention is, when I refer to a forward reference label, I define it right away, so I don't forget to define it later. And then over here, I'm going to comment out, I'm going to put some comments in to say, this is the else case. So at this point, you have a choice. Okay, if you want to preserve the order of the C code, then you can do a JMPI to the else case of what if n does not equal to 0. Okay, so basically you can jump to a label called do copy. Okay, that so that you can preserve the same ordering as in the original C code. So let's go ahead and do it this way because I think it's better to preserve that. So we're gonna have a do copy over here as a label, and then return dest is gonna it's gonna have an unconditional branch to all the way to the end of text string end copy. So we go to end text string end copy to basically mark the end of the entire logic here. So I'm going to put that label all the way here and say this is the end of text string and copy. And then at this point, I'm going to remind myself to do the usual return to caller. Okay, because if I don't remind myself, I might look at this code and go like, oh, I'm all done. And then when I run this code, it's not going to work. Okay, so now I go back. So I basically make the framework of the code first, and then I go back to fill in the details, once I have the framework. All right, so first we have to say, how do we return destination itself? Well, we just have to get the parameter destination into register A, and we're all done. Okay, so that's not too difficult to do, except we still have quite a few instructions to get it done. So LDIA with destination, and then we'll do the add instruction. Ah, okay. Add AD. So at this point, A is going to be the address of destination, and then we have to do a LDAA. So the A is now the dereference of the address of destination, which means A really is destination itself. Now you have to remember destination itself is a pointer. It's okay. I don't really care what it points to because in the C code, that's all I'm returning. Let me point out what C code we are talking about. We are talking about this particular value. It's just destination by itself. So at this point, we are ready. Okay, so we can now comment and say dest is in register A, ready to oops to return to caller now. Okay. All right. So that's one. What if we have some bytes to copy? That's what do copy is about. Okay, so the first thing we need to do is to copy whatever source is pointing to whatever destination is pointing to. Um, is it using a tab character again? Nope. Okay, that's good. Um, hmm, okay, that's fine. So we'll go ahead and implement this code here. So we have to find source first. Destination is not in any particular register, so we have to compute everything from the beginning. So we're going to do LDIA source add. That's a tab character because we were searching for tab earlier. So I'm going to do one last round to replace all the tabs with spaces later on. So we're going to add register the stack pointer to register A. So the A is now the address of parameter source, and then we'll do a LDAA. So the A is now source, but we cannot stop here because the right hand side of the assignment is not referring to source but what source is pointing to. So we need another LDAA here so that register A is now whatever source as a parameter is pointing to. So are we good so far? Are there any questions? No questions? Not
Can
yet.
you say that last load bit again, please?
The last load. Okay, so read the C comment on the right hand side of each line because that should follow. I mean, each one is based on the instruction before that. So if you're asking me that question, that means you may not be understanding one of these instructions of what it is doing. And we can refer to line numbers. Because what we need to do is to keep track of what is actually in register A after each line executes. And then the C comment, okay, the stuff after the slash slash is my way of documenting what is in register A. So, are there any questions about that part? Yes, LDAA is dereferencing, which is pretty well documented in the opcode table. All right. So I do hope you guys study a little bit because I think this stuff is already discussed before, or at least it is in the lab. Um, and also the opcode table documents every single instruction of what it does. So it's really helpful to kind of keep that in mind as well. All right, so A is good. We have the right hand side of the assignment in register A. So now we need to deal with the left hand side, which is about the same thing. We're going to use a different register this time. Okay. And then we have LDI, whoops, not LDI, but we have add BD this time. So the register B is now the address of destination. Then just like the other one, we have a LDBB. Okay. So the B is now the actual destination, the parameter, the value of the parameter. But we don't want another LDBB again, because another LDBB is just going to say, hey, register B now has the value of whatever destination is pointing to. I'm not interested in what it is pointing to right now, or the value that it's pointing to right now. I'm going to change it. So that's why we need a store instruction. Okay, so we're going to store whatever A has into register B. So this instruction is basically doing, let's dereference destination and then change whatever destination is pointing to with whatever A has. But whatever A has is whatever source is pointing to. So that accomplishes this one assignment operation that is commented out on line 28. Do we have any questions at this point? No question. All right. All right. So then we have to evaluate another condition over here. So we have to say, well, is the byte that we just copied, is that null? Okay, that's basically what the question is. Well, fortunately, it is still in register A, so I don't have to recompute everything. I can just say AND AA to evaluate or to test whether register A is 0 or not. And then we have the usual stuff, which is JZI. Okay, we branch if it is 0 to just return destination. Okay, because if that is the case, we're done. We're just going to return destination. And this time I can just jump to return destination, which is a label all the way here on line 20, because that's the stuff that we need to do. So I don't want to kind of repeat doing all that stuff. So is that okay? Even though it looks a little bit spaghetti. No questions? All right. Yes, and I did mention that this code is a little bit spaghetti because it really is. Okay, so if we do not go to return destination, then we're gonna have to evaluate the recursive call here, which is really kind of fun because we have to get back to every single argument and then make a little bit of a change before we push it on the stack, which might seem like, oh, okay, it's all that stuff of accessing the parameters again. Yes, there's that, but there's also a little bit more stuff to this. Okay, so just kind of stay with me here. Okay, so we're going to do the usual stuff, okay, which you already know is LDAN add AD. Okay, and I always kind of comment what A has at this point because otherwise I can lose track of that. So now we have LDA with A. So the A is actually the value of parameter n, but that's not what we want to push on the stack because we want to push n minus 1 on the stack, so we decrement A before we push it on the stack. To push something on the stack, we have decrement D and then stda. Okay, so this accomplishes pushing n minus 1 on the stack. Okay, no big deal. Okay, so now we want to push source plus 1 on the stack. So we're going to do about the same thing. Okay, and then we say LDAA, and then we say increment A this time because we want to push source plus 1 on the stack, decrement D, and then stda. Well, there's a problem now. Okay, this code is not going to work. This is not going to push source plus 1 on the stack. So does anyone want to explain why this is not going to work? It has to do with the assumption of what source the label is representing. Anyone? No one. Okay. So if no one wants to,
Oh, you mean like the offset
the
is
offs
now, yeah.
exactly. Okay, Hugh got it. Okay, so Hugh is remembering that we just pushed one more thing on the stack. How do we know that we just pushed one more thing on the stack? Line 47. On line 47, we decrement D again. So this changes the offset to every single thing by 1. Okay, what we knew as source is now source plus 1 because the stack pointer is decremented, but the location of source has not changed. And since the label source is where source can be found relative to the stack pointer at the entry point of the subroutine, the stack pointer is no longer at where it was at the entry point of the subroutine. It is now pointing to 1 byte below where it was pointing to at the beginning of the subroutine. So we have to add this 1 to compensate for the argument n minus 1, n plus n minus 1 that we have already pushed on the stack. So are there any questions about this part? So this ends up pushing source plus 1 on the stack. So are we good here?
Yeah, just confirming. We can just say 1 plus to increment the not the what's the word?
Yes.
Label.
Yes, you can. So you can do one of two things, or well, you can do even more. But the two most obvious answers is you can do the usual LDI A source on line 49, and then do an increment A after that, because that really is going to do exactly the same thing, but you're wasting an opcode when it is not needed. Because source 1 plus is evaluated by the assembler, it does not generate any additional opcode that runs during runtime. On the other hand, if you use an increment A between line 49 and line 50 at this point, that generates one additional opcode that will use up execution time during runtime. So is that okay?
Okay.
Yep.
Okay.
Yep. But it will still work if you do an increment A and get rid of the 1 plus on line 49. It's just not as efficient. All right. So now that we know this trick, now we can say LDI A dest 1 plus, or it should be 2 plus now, because we got 2 extra things on the stack compared to the entry point of the subroutine. So now the offset is 2 plus. Okay, we need 2 bytes. There are 2. Okay, how should I put it? The stack pointer is now pointing 2 bytes below where it was pointing to at the entry point of the subroutine. So we have to remember to add that offset, the additional offset, to the label. Then we can do the usual stuff. Okay, we can do the add AD LDAA, and then we have to increment. Okay, we have to increment A because after all we want dest plus 1. So we increment A and then decrement D because we have to reserve that space on the stack first. Store DA so that we push destination plus 1 on the stack. Do we have any questions at this point? This program is significantly more complicated than your swap subroutine, but I'm using it also to illustrate some of the tricks that you can use in your particular subroutine. So do we have any questions at this point? Nope. Okay. So with all of this stuff done, we are now ready to actually call whatever the subroutine is. Okay, the subroutine is tax string and copy. So we will just go ahead and make a call. So you already know how to make a call. Load the return address. Oh, excuse me. We have to decrement D first. Okay, this is order specific because we use LDIA dot 5 plus. If I switch the instructions so that we decrement D after the LDI, then I have to specify LDIA with a dot 6 plus because I have to account for the location of the decrement D instruction as well. And then we can do the usual stuff, store to where D points to, the return address, which is now in register A, and then the JMPI instruction to continue execution at the subroutine, which turns out to be the same subroutine that I'm in at this point. Okay, but that really is not important. Okay, when we get back, we're going to get back to the instruction on line 67. So we have to clean up the stack at this point. Okay, so we're going to clean it up by incrementing D 3 times. So is it faster to increment it 3 times, or is it faster to load one register with 3 and then add it to D? Well, I mean, they boil down to about the same. So I'm just going to increment D 3 times to get rid of all the arguments that are now on the stack. So now that the stack is totally balanced on line 70, I got one thing that I need because I'm still using the return value of this recursive call, and I have to remember to subtract 1 from that return value to become my own return value. So can someone tell me what I need to do at this point? No questions? Okay, so let me answer Ramsey's question first. For ease, can we use register C to store the address of the return and use that to reference the original stuff? But we don't need to refer to any original stuff because we are taking the actual return value of the subroutine, subtract 1 from it so that it becomes my own return value. Hugh has a different question. If we know the amount of local variables needed, should we allocate that first and then set the offset label accordingly? The answer is yes. So the offset should never be negative because you do not want to access anything that is below where the stack pointer points to. Does that answer the question, Hugh? Okay, great. All right, excellent. So now we can continue with this program. So at this point, I just have to, getting back to the original question, how do I subtract 1 from the recursive call to tag string and copy? Well, the return value is in register A, right? And we just need we just need to subtract 1 from that. So that means decrement A will do the trick. Okay, decrement A is going to say, A eventually will now be tags string and copy blah 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 -1. Okay, and at that point this is ready to end, also to go to the end label. So I'm just going to let it fall through because there's no additional code after this point. So I'm just going to let it fall through, and now I replace the to do with the actual code to end the subroutine call. But at this point, all I need to do is really just to pop the return address and then jump to it. So that means I just need an LDB with D, increment D, and then JMPB to return to the caller. That's a really kind of typical return sequence of code at the end of a subroutine. So, are there any questions about the implementation of text, string, and copy? I hear a mic popping, so I think somebody might have a question. Go ahead. No one. Okay. All right. So now that this is done, we still have to go back to main and then do some additional coding here. Okay, so here's main, and how do we reserve 20 bytes on the stack? Okay, in other words, how do we allocate those 20 bytes on the stack? Well, we do this. LDIA with 20, and then we do a subtraction. Okay, we subtract 20 from the stack pointer. This is how we reserve 20 bytes on the stack. Unfortunately, the toy processor may not have enough RAM locations for this, so I'm gonna have to shortchange this program a little bit and just reserve 8 bytes, and then I'll change the C code accordingly. 8 bytes is more than enough, but I still have to illustrate how it's done. And then we have to subtract another 1 byte for result. So this one I can just do using a decrement. Okay. But what I want to do now is to also give labels to all the things that I have allocated on the stack from the perspective of main. Okay, so where are these things located at this point? So can someone answer the question of what is the stack pointer pointing to at this point on line 87? What is it pointing to? What was the last thing that I allocated for? Come on, you guys, you can answer this question. Not the 8 byte array. The last thing that we just allocated on line 85 is result. That is what we just allocated. Okay, so now it points to one past it. Yes, which is the address of result. Okay, so at this point, register D, which is our stack pointer, really is pointing to the local variable result on the stack. Okay, so from this perspective, that means result is 0 byte away when I'm done allocating everything from where the stack pointer points to, and then buffer is result 1 plus because the size of result is just 1 byte on the stack. So this is how I would define the labels corresponding to local variables in main. Are we good so far? Maybe. All right. Okay, good here. Okay. So I'm gonna give you guys the code after we check everything, make sure it runs, okay, so that you guys can actually dissect this code yourself and add your own comment to this code, okay? Because I think that's how we study. That's how I would study for this class, is to dissect a program that has, yeah, somewhat, scarce, commenting, and then make it your own by adding your own comment to it, okay? So we'll go ahead and do the first call. Okay, so here's the call that we need to implement. We have to allocate the space for ABC and so on and so forth. So I'm going to show you this kind of nifty trick here, which is uh, some people can say it's nifty and some people can say, that is not cool. Okay, but regardless, okay, I'm going to show you this trick. So what I'll do is I'm going to do a JMPI instruction to underscore underscore, I would say cont1, okay, which is, it's just a continuation label here. So we'll put underscore underscore cont1 over here. So that means I can put something over here now, okay. So what I'll do is I'm going to define the array over here. So I will give it a name, okay. I'll call this literal string 1, okay. I'll give it a label because I need to go back and refer to that label. So now I can say 97, which is the ASCII code of B, 98, which is the ASCII code of B, 99, which is the ASCII code of C, and then a null terminator. Don't forget the null terminator because otherwise it's not going to know when to stop. Okay. So now with continuation label 1, I can now continue with the code. First thing I need to push is 5. Okay. So we'll go ahead and LDI A5, decrement D, STDA. So this is going to push 5 on the stack. LDI A with underscore underscore literal string 1. So underscore underscore simply means that label does not correspond to any concept that has a name in C. Okay, so I'm using that as an indicator that is an internal label that does not correspond to a particular named concept in C. So once again, we need to push it on the stack. So decrement D, stda. Okay, this is our source string. So basically, we're pushing ABC as a literal string on the stack at this point. So it is important to understand that when we pass double quote ABC as a parameter, we are not pushing the individual characters on the stack. We're pushing the address of where those bytes can be found on the stack. Alright, so the third thing we need to push on the stack is the destination, which is our buffer. Okay, so now we need to calculate the address of buffer, which starts with LDI A and then buffer. But remember, our stack pointer has decremented twice already at this point compared to the reference point where these labels are are defined. So that means buffer 2 plus is actually what we want because the stack pointer is now pointing to 2 bytes below where these references were made. Okay, so we need a 2 plus at this point, and then beyond that it is really just the usual stuff of adding the stack pointer to register A, and then we don't need to dereference anymore. Okay, because when we push buffer on the stack, we're pushing the address of buffer on the stack. Even though in C code it seems like we're pushing or we are passing buffer by value, You cannot pass an array by value in C or C++. So when you pass an array as an argument, you're always passing it by reference. You're passing the address of the array. So by this time, by the time we have the add AD instruction on line 106, register A actually has the address of the buffer itself already. So we're done passing all the parameters on the stack. Well, okay, never mind. Forgot about actually putting it on the stack. Okay, so now we are not good because we have to decrement D first. Okay, there we go. Okay, so line 107 is to reserve an extra byte on the stack, and then what line 108 is pushing the address of buffer on the stack. So now we are ready to call. Okay, so we just do LDI A again. Okay, excuse me, decrement D first. Keep forgetting that. LDI A with .5 plus, which is the return address, and then stda to actually store it to where the stack pointer is pointing to. JMPI, continue execution in the called subroutine. And when we come back, we have to increment D 3 times because the arguments are still on the stack. So we'll do it 3 times. And assuming this is all we want to do, it would appear that, hey, it's time for the halt instruction. Well, not entirely, okay? Because we haven't really cleaned up the stack entirely. Can someone tell me what is still on the stack that has not been deallocated at this point? You kind of have to go back to the earlier point of what we allocated on the stack to begin with. Exactly, you got it. Okay, so the local variables result, which takes only 1 byte, and buffer, which takes 8 bytes, they're still on the stack. Okay, so that means we have to deallocate those things on the stack at this point. And there are, let's see, several ways to do this. Okay, in other words, the question is how many bytes should I take away from the stack at this point? And yes, I know what is 8 plus 1. Okay, that is not the issue. So the issue is how do we write this program so that we can make it as self-contained as possible, so that if I do decide to change the size of the buffer, I don't have to go back and change a lot of lines of code. And if I don't, something is going to have a buffer overrun and causes all kinds of issues. So what we'll do is we're going to use a concept that C already has. Okay, we define buffer size to be 8. Okay, so if I define buffer size to be 8, then there's no reason to refer to the literal number 8 anymore, because everywhere where 8 is, I can just say buffer size. Okay, so at this point, okay, so when I get back to the end here and I need to deallocate the local variables, okay, deallocate local variables, I can do one at a time, but I can also do both at the same time. So I can do LDIA, and this time it is buffer size, which accounts for the buffer itself, 1 plus. Okay, the 1 is for the result. Oh, I take it back. I'm supposed to store the return value back into result, okay, because that's what line 92 is saying. So I better do that too. So we'll go ahead and do that, okay. So we have to compute the address of result in this case. So we have a LDI A. Nope, I cannot use A because A has the return value at this point. So I have to use LDI B with buffer. Nope, result. Okay, result is on the left hand side of line 92. Add BD. And this time I don't want to do LDBB because LDBB is going to retrieve whatever is in result at this point. Result is not an initialized variable, so I'm totally not interested in whatever result has at this point. Instead, I want to store to result with the return value from the subroutine. So that's what we're going to do. So now we finish the entire thing. Result equals to text string and copy blah blah blah. Okay. All right. So now we deallocate all the local variables. LDIA with buffer size 1 plus. Can someone tell me whether I should be adding or subtracting, adding to or subtracting from the stack pointer on line 125? We're trying to deallocate. We should be adding. Very good. Okay, so we add. to the stack pointer, whatever is in A. So the claim is by the time we get to the halt instruction, the stack pointer D should be back to where? It has to go back to the initial value of the stack pointer before main gets control. So where would that be? It should be getting back to 0. Good job. Both Angel and Nick answered this question. Very good. All right. So is anyone going to just say, well, we can trust Tack. This program took him about an hour to write, so it has to be right. It has to be working correctly. You don't trust anyone. Okay, very good. Okay, I don't trust myself either. We really want to see this code execute, not only to see if it runs correctly, but we might also want to look at how the stack is being used. I might be running out of stack space with this one, so we'll find out for sure. Okay, so we'll save this code. Okay, when in doubt, test. Yes, so when you test, you kind of have to know what the program is supposed to do, which was why we ran this code in C first. Okay, because that told us what the program is supposed to do, so that when we run this in assembly, what we see in the trace should resemble what we saw earlier when I ran this program in GDB when the program was compiled in C by C.
Professor, you mentioned that you might be running out of stack space for this program.
Yes.
Is there a way we can determine how much stack space we have? Do we just say, hey, there's this much space in RAM, this is how many lines of code we have?
Okay, so Hugh has a suggestion. Some lines might need. Okay, so each line can only take about 1 to 2 bytes. Okay, the worst is 2 bytes. The best is 0 because I do have some lines of comment. So we probably have close to 100 and something bytes as the code of the program. So now we have to look at how much stack space is going to be used using by this code. So I'm just going to attach that analysis here. Okay. So main is going to take up 8 bytes for the buffer, and then 1 byte for result. Okay, and then it is going to take up 3 bytes or 4 bytes to call string and copy the first time. 3 bytes for the 3 arguments, and then 1 extra byte for the return address. And then after that, string and copy will call itself, and every single time it calls itself, it's going to use up an additional 4 bytes, 3 for the arguments and 1 for the return address, and it's going to call itself, 3 times. So we are looking at a grand total of 13 plus 12, which is 25 bytes. Okay, so we are using up maybe 25 bytes, on the stack. So that means starting at location 255, we are gonna get the stack pointer to decrement back to location 230. I think 230. That's decimal. So I think we got plenty of space left. Nothing more than 2 bytes. That is correct. So LDI, JMPI, JZI, those will take up 2 bytes. Byte itself is going to take up only 1 byte per line. So when we only have 127 lines, including comments, even though some of those lines may take up 2 bytes, most do not. Okay, so if an instruction does not end with an I, it does not take up 2 bytes. Cool. Okay. So,
and
yeah, go ahead.
And Professor, it takes up 2 bytes when it ends in I because there's an immediate there that's taking up the next byte.
That is
awesome.
Correct. Yep. Because
and then so this is just a thing we should just always be doing when we've got long programs. We should be judging about how much space it's got and how much memory we're going to need for the stack to see if we're going to overflow.
That is correct. So this makes recursive subroutines kind of nasty because it depends on how you call the recursive subroutine, because that determines how many times it's going to call itself. So unless you are doing something like what this program is doing, where everything is kind of static and we can predetermine everything, if anything depends on runtime stuff, I'm talking about real life programs. So if anything relies on a value that is supplied by something other than the program itself, then it becomes kind of unpredictable. You can probably do a worst case analysis, but sometimes the worst case analysis is a lot worse compared to um, what the average case. But when you want to find out when you might run out of space, you kind of have to make your analysis the worst case analysis. So does that answer the question? Maybe. I hope so.
Yeah, that answers my question. Thank you.
Excellent. All right, so we're gonna exit this code, and I now remember I just looked up before the class, what to do on the command line to copy a file into the clipboard of a GUI. It's called xclip in Linux. So xclip-i, which means you'll take this file as the input. So copy everything from this file into the clipboard. Okay, which doesn't seem to show anything, but when we get to the assembler, we will see that everything is in the buffer already. So we'll go ahead and go get the assembler. Oops. Okay. And here. And then we go to the assembler with postfix expression. And then we go ahead and paste. No, no, that did not work. I thought everything was put into the clipboard, and it did not actually put it into the clipboard. Ah, okay, so that means I just have to do it manually. Where's my, there we go. Alright, so man xclip. Well, I'll do it maybe some other day. Mouse pad it. Oops. There we go. It's off the screen, but it's okay. All I did was to copy and paste everything. So it's gonna be okay. It's interesting how the assembler did not complain about this line, even though it's a hyperlink to something. Oh, you know what? I know what it's trying to say. It's considering HTTPS as colon as a label definition, and then the slash slash begins the comment. Okay, you guys don't find it funny, but I find it extremely funny that HTTPS colon slash slash is interpreted quote unquote correctly by the assembler as the label definition of HTTPS. Okay. There we go. So we got all the code in. We'll finish, let it finish, so that we can check. No, no. Okay, that's good. Yeah, that one day in the lab, when the assembler stopped working, that was a Google issue. It was resolved mysteriously the next day. Alright, so we can save the file as string and copy.csv. Okay, so now we're going to run the program on the command line, and we'll see how many people remember how to do it on the command line. It's java-jar, and we have to first find the logicium jar file. Then we have to supply the circ file for the processor, okay, which in this case is kinda in the same folder, but it's inside a sub folder called processor, and then processor 0003.circ. Then we specify -tty to specify that we do not want to start up the GUI. Oh, okay. xclip-sel. Okay. Okay. Well, thank you, Hugh. Table, and then Nick said that's one too many zeros. Nope, 3 zeros is correct. and then dash load, which is the name of the RAM file. It is string and copy.csv, and we want to redirect the output, which in this case is going to be a little bit messy, to log.tsv, and we'll let it run. All right, so it did terminate. Okay, now we put it into the trace analyzer. So we have file import. Here we go. Alright, so when the spreadsheet is really busy, processing the import, let's think about how we can check whether this program worked or not. In other words, how do we examine the trace and figure out, did it actually copy those 3 characters on the stack? And if so, where is it supposed to copy those 3 bytes on the stack, or 4 bytes, because we also have to copy the null terminator. And then we also have to say, what should be stored in result? Okay, so those are all the questions that we want to ask ourselves when we test run the program, is how do we know the program is doing it correctly? Okay, and to illustrate it, let me see if I can bring up, I suppose I can bring this up. Okay, so we'll clear all this stuff. So what we'll do is I'm going to go through a manual process. The trace analyzer is all done, okay? But before I look into the trace analyzer, I want to figure out what is on the stack, okay? How do I know this program runs correctly? So we're going to look at location FF, FE, FD, FC, FB, FA, F9, F8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, um, but this is really just for checking whether the entire program works or not. So it's not even to test whether, to check whether each call is working or not. So these 8 bytes, okay, 1, 2, 3, 4, 5, 6, 7, 8. These 8 bytes belong to buffer, okay, which is in main. So if the copying is correct, we are expecting 97, okay, this is decimal 97 to be here, which is ASCII code of A, 98, which is B, supposed to be here, 99, which is C, is supposed to be here, and then this byte is supposed to have the content of 0, which by default already has a content of 0. So it's hard for us to check whether location FB, whether we actually copy the null terminator or not, unless we check whether the instruction executes or not. Okay, um, F7 is our result. Okay, so the result is supposed to be the return value of string n copy, which in return is supposed to be the destination. The destination is buffer. So F7, at location F7, it should have a value of F8 in hexadecimal. And if you want everything in hexadecimal, let's do that. Okay, this is 61, 62, 63 here. Okay, so at the minimum, okay, at a minimum, this is what we need to confirm, is F7 is finally going to store a value of F8, and then F8 needs to have a content of 61 and so on. And then the stack pointer should be balanced. In other words, if I look at the last update to the stack pointer, it should be an update back to 0. Okay, so those are the minimum things that we should do with the trace analyzer. Okay, so we're gonna check that. Okay, we go to analysis, and what we need to do now is to go all the way to the end of the program, or to be more specific, I just need to know whether the stack pointer gets back to 0 or not. So we'll go ahead and search for that. Okay, so we go to edit. Come on, let me click. Alright, there we go. So we go to, then we look for register D, which is the stack pointer, getting back to 0. Okay, so we look for D equals to 0, and I think it might be a single 0. Nope, it's a double 0. Okay, there we go. Click done. So this should be the last update of the stack pointer. And you can see that this time, when we update the stack pointer, the flags got changed, whereas before it never got changed. That's because in all of our other programs, we increment the stack pointer back to 0, and increment does not change the flags. This time we were using the add instruction, and the add instruction does change the flags. So, and that should be the last update to the stack pointer, which also means
And
question.
Professor, we're using the add instruction specifically because it's not we're not just incrementing it by.
Yeah,
Why exactly are we using the add instruction? Oh, is because we're incrementing it by
by
the
9.
full size of buffer
Yeah,
rather than by
yeah,
1. Okay, yeah,
exactly.
cool. I
Yep.
just needed to say it out loud to get it.
Yeah, that's fine. And then after this, we don't have any more instructions because at location 6.8, we actually have the halt instruction. The halt instruction is at location 6.8. We can always double check that. Okay, so don't assume anything to be right. Okay, you always want to double check stuff. So we want to double check to make sure that the halt instruction is actually at location 6.8. So we have to scroll all the way down. So the program is not really quite as long as as I originally thought, because location 6.8 is 106. Okay, that's 106. So the program only takes up 106 bytes. Okay, um, but yes, double checking that the halt instruction is actually at location 6.8. So now we need to check. Okay, did we actually copy ABC at the locations that we thought that those bytes would be located? Okay, that becomes the next question. So let's go back to the home of this entire thing, and then we'll search again, Control H, and then this time we're going to look for location, whatever at location. um, I think F8 is supposed to get lowercase a, which is 6.1. Okay, so we're looking for something like this, and it has to be a single equal because we are not reading from location F8. We are actually overwriting location F8, so it is an assignment operation. Okay, press enter or click find, and here we have it. Okay, the next byte is 62, which is B, should be stored at location F9. Okay, and click find. Uh-oh. There we go. And then 63 should be stored at location FA. I don't know exactly why it did this. Hmm. It's right there under the find box. Oh, okay. Because it's yeah, this is the uncleaned up version of the analysis tab. I see. So we don't want it to search all the other sheets. We just wanted to search in. Oh, okay. Let me see if I can refocus to this one and then specify this sheet only. There we go. Yep, it found it. Nope. It should find it in the other sheet too. It's not in the analysis sheet. Hmm. Let me see if it's not matching case because it's not checked. So FA, well, I mean F was lowercase to begin with in all the other search. So this really should be reflected in the other sheet as well on the same row, which is 549. Alright, so let's try to solve this puzzle. Row 549. Oops. It's here. Very strange. Search is being bad. No, it's Google Sheet being bad. Okay, so it is all here. And we also want to know whether location F7 is storing F8 as a value. Well, Microsoft is actually using Google's code now, aren't they? I mean, Microsoft Edge, the browser, is using the Chrome engine, so it's really the other way around, which is funny, but not too funny. Okay, so we want to also look at location F7 and see what is in it. Okay, so this should be a little bit better. And this time we limit it to this sheet. Don't look anywhere else. Okay, fine. There we go. Okay. So we can also see now that location F7 does store a value of F8. So everything that we predicted prior to looking at the trace analyzer is found in the trace analyzer. Now this is really important because if I predicted something and it actually did not happen in the trace analyzer, that means somehow my understanding of the program or how it is supposed to run is different from the way it actually runs. So that clearly is something that we need to look into if that were the case. Okay. So the next thing we also want to do, okay, I know we are running out of time, is how many bytes ended up being used on the stack. I predicted 25 bytes was used on the stack. So the question is, was that it? Okay, did the stack pointer went as low as 256 minus 25? Well, let me see. No, 255 minus 5 minus 25. Um, so that's the question. Okay, when was the last update to the stack pointer? When it's at the lowest point? What was the lowest point of the stack pointer? So what we need to do is focus on column D because it reflects all the changes to the registers, and we want to focus on just how we update register D because that's the stack pointer. But we can also basically say, okay, we kind of know how far it should have gone, which is 25 bytes. So FF minus 25, which is 9, is how much? Okay, so let me show you how to do this by hand. Is how to do hexadecimal number subtraction by hand. So when we use a 1 byte, it is FF. So we're actually looking at 00 or 100 minus 25, and 25 is 19 because it's a 16 plus 9. These are all in hexadecimal. So the first digit or the least significant digit is a 0 minus 9. The 0 is less than 9, so we need to have a borrow. So that borrow is going to give us a 16. 16 minus 9 is 7. So here's a 7 here. And then we have f minus 1 because the 1 0 had a borrow, so it becomes an f. F minus 1 is an e. So I'm thinking the stack pointer should only go as low as e7. Okay, so we can go back to the trace analyzer, and this time we can just focus on column D. Isn't it minus 2? Because borrow and initial. Okay, so let's do this the long way. So we have hexadecimal 100 minus hexadecimal 19. Okay, so I'm using the same rows as usual. Okay, but this time it is a base 16 subtraction. Okay, and we'll figure out how this works. Okay, so 0 minus 9 clearly has a borrow, so there's a borrow over here, and then once we have a borrow, then digit 0 now has a value of 16. 16 minus 9 is 7, so we just have a 7 here, and then we have a 7 over here because the borrow from digit 0 should always be a 0. Okay, and question is because borrow and initial 19. That is correct. So 0 minus 1 is f, and it also has a borrow over here. F minus 1 is a e, and then 1 minus 0 is a 1, minus 1 minus 1 is also a 0. So E7 should be the location. Okay, but we can check. Okay, we now go back to the browser, and then we look up updates to the stack pointer. So we Control H, find, there we go. And we want to find D equals to E, what was it again? E7, there we go.
7.
Yeah, go ahead.
No, I was just trying to say it should be 7.
Oh, okay. Yeah, that tells you something about my my cache gets kicked out, kicks out all the pages pretty quickly. Okay, so we'll go find. There we go. All right, so we find that it did get down to, oops, location 7. The question is, was that it? Okay, let's Control Z because I accidentally typed something. No, I did something else. No, that's good. All right. So now we can search and see whether it decrement any further, which I do not think should happen. Okay, so we keep going, and the next update should go back up again.
Professor, wouldn't it just be easier to search for the value 1 less than we expect it to be? And then if we don't find it, then then we know that it hasn't gone below that?
But then I won't be scrolling around.
Hey, look, there's D equals E8. It went further.
Yes. No, it did not go any further. It went back up again.
Right.
So it only went as low as D7, which means we only used 25 bytes on the stack. Is that okay? Nick?
He responded in the chat.
Yep, I saw that. Thank you. So I think we should probably conclude today's lecture at this point, just because it's super long and it is just one single program. I will post this on as an announcement, kind of like the other one. And I'm not going to give you guys any new homework assignment, just because I think the swap subroutine probably will take you guys a little bit longer to write, and this whole program here is supposed to be a clue to help people to write the swap subroutine. Thankful for the convenience of high-level languages. Yes, yes, indeed. Yeah, so can you guys imagine, when okay, I know we are way out of the lecture time, so if you guys want to sign off, that's fine. Okay, this is not related to the class. Since there are no new labs, you don't have to worry about the passcode to the new lab either. But I do want to mention Unix, Bell Lab, and I think the last name is Richie, spelled this way. So when you look at those two guys who wrote the original Unix operating system, and Dennis Ritchie is usually referred to as the primary author of the original Unix code. So when he was trying to write Unix as an operating system, which is now a part of iOS, it is a part of OS 10, it is a part of the XP Unix system, it is a part of the, well, I think that's it. And then Linux is inspired by Unix, okay? And the only tool they had at that time to write Unix was an assembler. And they were targeting a platform that is the predecessor of the PDP-11 mainframe computer. So if you guys want to look it up, that's fine. In fact, that's funny. It's funny. They have an emulator of the PDP-11, so it can actually run the original Unix in the PDP-11 emulator in Linux. That's that. I mean, that to me is really funny. Oh, this is even better. It is a JavaScript program. Somebody wrote a JavaScript emulator for the PDP-11, which was the original quote-unquote mainframe computer that Unix was built on. So anyway, the bottom line, the bottom line was when when this guy, okay, who was a seasoned programmer, was tasked to write an operating system, even though the original Unix is not quite as complex as it is now, it is still an operating system. It is still pretty complex with a file system and stuff like that. He quickly decided writing everything in assembly language was not the way to go, and hence the birth of the C programming language. So this whole thing, I know you guys are thinking, okay, can we go to dinner now? But this whole thing, KNR is a Carnegie and Ritchie, I think. Is that right? I may not pronounce the last name correctly. So KNRC programming, and they wrote the original textbook, which I bought but never read. Yeah, so Carnegie. Carnegie is Brian Carnegie was the other person. So this is kind of like the full circle of everything. I just kind of felt that it was kind of interesting. So I'm gonna stop the live stream for sure. Okay, so I'm gonna stop the